Welcome back, everyone. I'm going to talk about ChemGPT. Long ago, people used to say things like, I won't believe in artificial intelligence until I see a computer beat a human chess champion. In 1985, Shu Fengshong, he started his PhD. His English name was Crazy Bird. He started a project in 1985. He started his PhD. This later on became called Deep Blue. In 1997, Deep Blue beat Garry Kasparov, the world chess champion. Then everyone started saying, I won't believe in artificial intelligence until I see a computer beat a human champion at Go. In Go, there's 10 to the 170 possibilities versus only about 10 to the 46 possibilities in chess. Another word for this, instead of saying possibilities, I can say legal board positions. That's another way that people describe this. So a computer cannot just memorize 10 to the 170 games. It has to actually be able to think. You might imagine that if a computer memorizes all possible games, then based on what the opponent does, then the computer just has to pick the right moves because it knows how every game unfolds. So that's not possible when there's 10 to the 170 games. There's only about 10 to the 85 particles in the visible universe. So if each of those particles was representing a 1 or a 0, you won't even have enough disk space to store all games. Even with 10 to the 46 possibilities, it's not really going to be possible to memorize all games on a realistic computer. However, the number of possible games can be restricted based on what realistic games are actually going to be played. So that 10 to the 46 can be brought down by several orders of magnitude, but when you start with 10 to the 170, there's not much you can do. It's like the computer actually has to think. It can't memorize all games and just act based on that. It also can't just follow an algorithm. Maybe it's not memorizing games, maybe it's following a very good algorithm, but it can't just follow an algorithm that's directly coded by humans, because it needs to beat the human. And these champions, the world's best players, if there's a really good algorithm out there, those humans would be following that algorithm. If we know such a good algorithm to code into the computer, the humans also know that algorithm. They can memorize it and try to follow that algorithm as well. And in 2016, DeepMind actually beat Lee Sedol. This used 1,920 CPUs and 280 GPUs. That's not a lot, okay? Most of you have access to Compute Canada machines now. Compute Canada has a lot of supercomputers. There's Cedar, Graham, there's Narval, Beluga. Cedar is just one of those supercomputers. It has 94,000 CPUs, 1,000 GPUs. So it has way more GPUs than DeepMind used, and about 45,000 times as many CPUs as DeepMind used. So we could easily do this in Compute Canada machines. Not that we would be allowed to do it, but because then we would be monopolizing the whole computer, and this is a supercomputer used by a lot of shared groups. But theoretically, this would be possible with the hardware that we have. Then people start saying, Go is too simple. I'll believe it when you beat a human at poker. And the reason for this is that Go has a simple set of rules. There's only a finite number of small, simple rules, and a computer can play an enormous number of games in a day. It's easy to code these rules and to have the computer play games all day long. So reinforcement learning is a type of machine learning where when you win, you get a good score. When you lose, you get a bad score. And you can play lots and lots of games. And when you play enough games, you learn how to get good scores. Eventually, you will know exactly how to win in this game. you can basically develop algorithms this way. So there's newer algorithms that the computer understands that the humans don't even know. They have not directly coded these algorithms, but they've coded reinforcement learning, which allows the computer to come up with better algorithms. The other thing about Go and chess is that they're for only 2 players. That makes things a little bit simple. 1 player, the opponent makes a move, and you make a move based on what the opponent does. In poker, you have multiple players. But more recently, there has been this paper published in Science, Superhuman Artificial Intelligence for Multiplayer Poker. And this is also more complicated than chess and Go in a different way, in that it's not like there's some optimal move at every step that the computer is trying to make. There's actually some randomness. The computer is actually trying to bluff in the most optimal way and make the other, try to fool the other players, right? So this is more, this is a different type of intelligence, you might say. It's about trying to make the other players bluff, not necessarily trying to make some optimal move. Okay, I learned about this when I sat in a lecture by Kate Larson, a professor at the University of Waterloo. Her supervisor was one of the co-authors of this paper, and I remember when she told us about this paper had just been published at the time, and she was very excited about it because her former supervisor was one of the co-authors. This is how that game turned out, the multiplayer poker game against the artificial intelligence. All 4 of these poker champions, they all lost big time. Okay, they all lost a lot of money. There once was a student who in May 2023 was asked to do geometry optimization for the beryllium hydride molecule at CCSD parenthesis T level with PySCF. He was a first-year engineering undergraduate student with 0 knowledge of computational chemistry, just like a lot of the people in this audience. First-year undergrads, maybe second-year undergrads, with 0 knowledge of what CCSD parenthesis T means, or what geometry optimization means, or any of these things. Now that student replied saying, I think it will be easier to use other software that supports analytic CCSD parenthesis T gradients to do this. For example, C4, MolPro, and NWChem. This student discovered on their own that PySCF cannot do analytic gradients for CCSD parenthesis T. But a lot of you might still be amazed at that because you don't even know what is meant by analytic gradients. What does that even mean? I was very impressed by this as well. Now that same student, because we can't do analytic gradients, the student was asked to code numerical gradients in Python to work with PySCF. But this code just seemed unusually complicated to me. It applied to N-atom systems, even though the assigned molecule was beryllium hydride. There's only one geometry parameter here, the internuclear distance r. For beryllium hydride, it's a diatomic molecule, so there's no angles, dihedrals, all those things. We don't have to worry about those. And this code was optimizing all these angles and dihedrals and everything. It was basically optimizing the geometry for an arbitrary N-atom system, even though the molecule in question was just beryllium hydride with one geometry parameter. So I asked, where did you get this Python function, numerical gradient? And his answer was, I wrote a version and tested and improved it with ChemGPT 4 to come up with the current version. So then I asked, was it also ChatGPT that told you that analytic CCSD parenthesis T gradients are only available in C4, MolPro, and NWChem? Now it starts to make more sense. At the beginning, I was absolutely confused. I mean, it's true that PySCF can't do analytic CCSD parenthesis T gradients. And analytic gradients would be helpful if you want to do geometry optimization. If you can find where the gradient is equal to 0, then you can optimize functions like that. And I do know that C4, MolPro, and NWChem can do analytic gradients at CCSD parenthesis T level. But how did the student even know to search for that? I mean, that just blew my mind. But now that I see that this Python program was written by ChatGPT, then I start to think, okay, maybe that's where he figured out that analytic CCSD parenthesis T gradients aren't possible in PySCF. And the answer is yes. ChatGPT told me that C4, MolPro, and NWChem are some of the available options. That's right. These aren't the only programs that can do analytic CCSD parenthesis T gradients. I wouldn't be surprised if Dalton and OpenMolCAS and other programs can also do it. So let's talk about GPTs. OpenAI's GPT-1 was developed in 2018. It was trained with 4.5 gigabytes of training data. Even you can do that, okay? Your phone has more than 4.5 gigabytes. Your phone probably has 16 gigabytes at least. And 1 month on 8 GPUs, that's a joke, okay? I told you, Cedar has more than 1,000 GPUs. GPT-2, 1 year later, it was trained from 40 gigabytes of Reddit posts with more than 3 upvotes. So by using Reddit posts with more than 3 upvotes, they have good quality posts. And I guess the Reddit posts are all openly available and they didn't have bot detection that stopped OpenAI from scraping the web or scraping all of their Reddit posts. 40 gigabytes is still nothing, okay? Your computer has enough storage space to store this data set of 40 gigabytes of Reddit posts. And 100 times more floating point operations compared to GPT-1. Still, 800 GPUs is not that much. Cedar has more than 1,000 GPUs. GPT-3 was trained with 570 gigabytes of data. Still, that's not a lot. 200 times more floating point operations compared to GPT-2. But 570 gigabytes as a data set, that is really not a lot, okay? These are just 3 of the supercomputers at Compute Canada. Cedar has 23 petabytes of project space. That means that we could store this data set, 570 gigabytes. We can store that 1,000 times, and we would still only have 570 terabytes, which is not even 1 petabyte. Okay? So the data sets, they're still small. In terms of Graham, I'll just give you some, since I'm talking about the Compute Canada supercomputers, Graham has 41,000 CPUs, 520 GPUs. These are spread across more than 1,000 nodes. 903 of the nodes are 32 core processors. They have 125 gigabytes of RAM each. Some of the computer nodes have 500 gigabytes of RAM. Some of them have 3 terabytes of RAM. Okay? Cedar has 4 nodes that have 3 terabytes of RAM each. There's also some 48 core nodes. And in total, you have more than 94,000 CPUs, more than 1,000 GPUs. So the compute power is not an issue here. For GPT 3.5, released in 2022, this is what's known as ChatGPT, or the first version of ChatGPT. The training data was not disclosed. The number of floating point operations was not disclosed either. But with GPT-4, which was just released 3 months ago, we know that there's 100 times more floating point operations compared to GPT-3. 200 times 100 is what? 20,000? 20,000 times 100 would be 2 million. So, is that right? 20,000? No, 20,000 times 100. Yeah, that would just be 2 million, right? So, 2 million floating point operations times 8 GPUs. I mean, this is 2 million times as much cost computational cost compared to GPT-1. So maybe 16 million GPUs is what you need. But that's still possible because we have 1,000 GPUs, and if those 1,000 GPUs are running for 1,000 months, then okay, it's getting difficult. But I think also the hardware is getting better from 2018 to 2023. So each of the 2023 GPUs are more powerful. They're doing more floating point operations per second compared to the GPUs in 2018. And the algorithms might also be faster. There's more efficient use of the GPUs. And, every year or so, the floating point operations on the top 500 supercomputers in the world, they don't go up just by 1 or 2 floating point operations per second. They go up by orders of magnitude. So it's not unsurprising the amount of floating point operations that were used in GPT-4 compared to GPT-1. And ChatGPT or OpenAI's GPT, these are not the only GPTs out there. So these are all examples of large language models. In May 2023, Google released a large language model called Pathways Language Model. Then there's, in March 2023, GPT-4 by OpenAI. But in the same month, March 2023, there's several GPTs that were announced, okay? Cerebras has Cerebras GPT. There's Falcon. There's Bloomberg GPT by Bloomberg LP. Huawei, the Chinese company, has Pangu Sigma. There's also Open Assistant. And Jan LeCun, not Fields medalist, Turing Award winner, which is basically like the computer science Nobel Prize. He won along with Yoshua Bengio and Jeff Hinton, won the Turing Award for deep learning. So this is an expert in deep learning. He works at Facebook, now known as Meta. He said he's been quoted saying that ChatGPT, it's not revolutionary in terms of the technology, the underlying technology or the algorithms. There's a lot of companies, so Google, Facebook, and a lot of different startup companies, maybe 15 different startup companies, they can all make ChatGPT on their own. It's just that ChatGPT happens to be well engineered. So it's not like there's any new algorithm that no one knows about. We all know how to make ChatGPT. It's just about good engineering, making something that's very user-friendly and works the way you expect. That's what makes ChatGPT stand out compared to all these other GPT models. How many people here know about Mid-Journey, other than Harvey Wilson that I showed this to? So anyone in the audience, can you tell me in the chat if you've heard of Mid-Journey, or unmute yourself, say something? I'm not seeing anyone saying that they've heard of Mid-Journey. Abdul is typing. Okay. So, okay, 2 or 3 people have heard of Mid-Journey. Now this is like ChatGPT for generating images. This is just a Discord server. You get on the Mid-Journey Discord server and you ask for a reassuring, smiling Japanese family in front of a house wearing casual clothing. It has to be a realistic photo and an elderly couple. And the result you get, after not much time, is you get 4 examples of smiling Japanese families. They're all elderly couples wearing casual wear. If I were to search for this on Google Images, I don't think I would find these, especially with search like this. Okay, I've given up on giving such detailed searches like elderly couple, reassuring family, Japanese, casual wear. I don't even look for that. I just search for Japanese family outside of their house, and then I get a lot of images, and then I have to do a lot of work to find the images that I'm looking for which I'm looking. And I might do a few iterations. I might see something that I like, and then I click on that, and then Google Images suggests some other images, and then I converge on something. I have to do a lot of work. Here, Midjourney finds you the images right away, but it's not finding existing images. These images didn't exist before we made the query. These images were generated. It's artificial intelligence. So just like in ChatGPT, you ask for an essay and it gives you an essay. Here, you ask for an image and it gives you the image with the description that you gave. Here, we ask for a good-looking black senior executive at a networking engagement with professional photography, high definition, style has to be realistic, aspect ratio 3:2. There we go. 4 different black senior executives with professional photography. If you have an SLR camera, you probably know that you can focus on one person and all these people in the background are blurry or not focused at least. Okay? So that's exactly what we asked, and that's exactly what we got. These people do not exist. Or hopefully they don't exist. Hopefully Midjourney is not just finding an image and repeating it. Here we have a much more detailed description. A very handsome black senior executive delivering a keynote speech at a leading tech and telecommunications summit. The backdrop can include a large screen showing futuristic telecommunications network images or technological innovations. The audience is filled with industry professionals listening attentively, capturing the executive's influence and leadership. Professional photography, cool tones, high definition, style equals realistic, aspect ratio 3:2. And here we go. In the background, we have, the backdrop can include a large screen. Here we have a large screen with futuristic telecommunications network images. That's what the artificially intelligent software came up with. This is what they think network images look like. What I found particularly interesting was that it was supposed to have an audience filled with industry professionals that listen attentively. So why is this guy sleeping? So I won't believe in artificial intelligence until this works. You can beat humans at chess and Go and poker, but if you don't understand what I'm asking, then how are you really intelligent? You're just doing what the training data told you. So the training data, in every conference there's at least one person sleeping. So I guess the artificially intelligent software thinks that in order to have a proper networking event or a keynote speech, there's got to be at least one person sleeping. Or maybe because there's so many people sleeping in the training, maybe because so many people... So Sukrit says he can't see the image. Is anyone else not able to see the image? Gareth is also not able to see the image. That's true. Actually, I can't see it on my other computer either. So, how about now? I don't know why it's not loading. Yeah, no one can see this image. Let's try again. View presentation. Yeah, I don't know why it's not showing the image. It's basically stuck now, right? It's not showing anything anymore. It's not showing anything beyond... I can reshare, that's what I will do, okay. So, stop streaming and start streaming again. Allow. Share the full screen, allow, and we'll go back to here. Presentation, and here. Oh, it's still not streaming. It's stuck at, okay. So now you see the image. Okay, so here it is. So what I found fascinating was that it says the audience is filled with industry professionals who listen attentively. So why is this person sleeping? That's still not, there's a circle around this guy over here, and that's not updating. I'll try one more thing. So I'm using Ocular right now. That's because it was taking long to load Google Slides. Google Slides is what I used the last few times. And it worked fine. So I'll exit this. We'll try Google Slides, because that's what I was using all the other times and it worked perfectly fine. It's just that it's loading so slowly for me today. Google Slides is just loading so slowly for me today. And you can't even see my screen again. I changed my screen and it doesn't update. Stop streaming. Okay, we'll try again. I think maybe my internet connection is slow today. That might be the issue. ChemGPT, here we go. So I'll try sharing again. Are people able to see my screen? Or is it just two purple dots? Okay, it looks good on my other computer. It's just taking so long to load. Okay, let me send you the PDF and you can follow along the slides. Yeah, you can follow along the slides. So I can see the slides, so I can still go through my presentation, and you can try to follow along the slides rather than hearing me talk about things that you can't see. So I guess they would be in downloads. So the PDF should be in the chat. It's still taking so long to upload, and you can't see my screen again. So that's, I guess that's an issue. I don't know why you can't see the screen. I've done so many presentations here and it's never been so slow. The uploading of the PDF is taking forever. Okay, the PDF is uploaded, so you now have the PDF. You can go to the full screen or presentation view, slideshow view, whatever, and you can get to the slide where I was. And are people still able to hear me?
Yes, I think so.
Okay, excellent. So everyone can still hear me, that's good. And you have the PDF now. So then let's just get back to that slide. And let's just go from there that way. You can't see my screen, that's too bad. I'll still share my screen just in case. So I'll share my screen, entire screen, share. Okay, now Google, okay. Yeah, Google's taking forever. And my stream is still not shared. Okay, watch stream, let's see how this works. Okay, so can everyone see my screen now? Can everyone see my screen? Okay, let's go back to where we were. Oh, too bad when I changed the slides, it's not updating on my other computer. So at the end, it's going to ask you to do a survey, like to rate the quality of this stream. Everyone can put 1 out of 5 or 0 out of 5 because this is not working very well. So anyway, so I'll just get to the slide on my local machine and you can follow along your copy. Yeah, it looks like the screen is showing like a transition screen where I was transitioning to a different slide. I hope it wasn't happening that way the whole time. Okay, anyway, so I'm on this screen with the 4 very handsome black senior executives. Underlined, I say, the audience is filled with industry professionals that listen attentively. And here you can see someone sleeping. So I won't believe in artificial intelligence until this works. Because the artificial intelligence in this case seems to have been trained on some images of, well, all sorts of images. And at every conference, there's someone sleeping there, right? So it picks up on that and thinks that this is what conferences look like. And it doesn't realize that this person is not listening attentively. So it doesn't really know what it's doing. It's just basically following some algorithm, and based on the data set, it's giving you some something based on the data set. It's maybe partially intelligent, but still not as good as a human in terms of being able to know what the person is asking for. It's able to generate the artwork very fast compared to a human, but it's not generating the correct thing. But still, it's very impressive, okay, to be able to make these images just based on a search prompt. So I'm on the next slide now. How is this done? Just like with GPTs, there's lots of different types of GPTs. There's the Bloomberg GPT and the ChatGPT and different large language models. For image generators, there's Midjourney. Stable Diffusion, DAL-E, those are just 3 examples. Stable Diffusion version 1 was trained with 600 million images. That's 150,000 GPU hours on NVIDIA A100 GPUs. Now, if you see the next slide, you see Compute Canada's Narval has the same GPU, NVIDIA A100 GPUs, okay? It has 4 of these on each node, and there's 159 such nodes. So if you have 150 GPUs, so if you take 1 GPU for each of these nodes, you have 150 GPUs, and if you spend 1,000 hours calculating things on those 150 GPUs, then you have only 41 days of human time or real time to get this 150,000 GPU hours, okay? 150 GPUs times 100 hours will give you 41 days. That's 150,000 GPU hours. If we were to use all 4 GPUs on the 150 nodes, then we have 150 nodes times 4 GPUs. Then we only need 250 hours of wall time, and we have 150,000 GPU hours. So this will take only 10 days. So you can make version 1 of Stable Diffusion on your own in 10 days with Compute Canada resources if you wanted to. Stable Diffusion, I believe, is now on version 2. So it's not that big of a leap to go from the state of the art, whatever they have. You can probably do it with the computer resources that we have. How about the performance on science questions? This is important because it looks like we can make state-of-the-art large language models or image generators with the computer resources that we have. We can make our own ChatGPT, one where you don't have to give your phone number and all that. We can make our own Midjourney or Stable Diffusion. We have the computer power for it. The algorithms are known. It's all published in the literature. We can read how it works and we can do it. So then let's see how it works on science questions. Now, So Chow was doing calculations on the oxygen molecule, the oxygen atom. And he asked me what the charge should be. What should he set charge in PySCF? And I wonder what ChatGPT and Google say when you ask, what's the charge of an oxygen atom? And you can see, he answers that Google apparently says -8 and ChatGPT says 0. I tried this myself in Google. What's the charge of an oxygen atom? And indeed, it highlights -8. I didn't highlight that myself. That's just what it gives you. So Google, it's smart enough to know that the oxygen atom has 8 electrons and that the nucleus has a charge of +8. But it's not smart enough to put 1 and 1 together and say that, and just give a crisp answer that the oxygen atom has a charge of 0. ChatGPT wins. ChatGPT gives the correct answer here. So ChatGPT 1, Google 0. Eamon was using ChatGPT to find out what n roots means in PySCF. And the answer she got was n roots equals 3 corresponds to the 3 lowest lying excited states. That is wrong. N roots equals 3 means you're finding the lowest 3 roots of the Schrodinger equation, the lowest 3 energies of the Schrodinger equation. The lowest energy is the ground state. The next 2 roots are the first excited state and the second excited state. The first 3 roots are the ground state and the first 2 excited states, not the 3 lowest lying excited states. And I'm not cherry picking here. If you've been following the discussions in the Discord server, I'm basically giving you all of the ChatGPT conversations that the students have had. Jack was the first, second was Su Chao, third was Amun. I'm going in order. Every single person has use chat. Well, So Chow got the right answer for that very simple question about the charge of the oxygen atom. But everyone else is getting bad results here. Well, Jack got good results. It's true that PySCF can't do analytic gradients for CCSD parenthesis T, but it didn't know that PySCF AD can do automatic derivatives, and it didn't know that it gave a really bad code for geometry optimization. And Amun's first questions didn't turn out very well either. ChatGPT is giving the wrong information. Here again in Amun's conversation, in the scf.uhf method of the PySCF package, by default, only the lowest energy excited state is computed. And Amun asks, first excited state or ground state? By default, is it the lowest energy excited state that's being computed, or is it the ground state? And ChatGPT says, apologies for the confusion in my previous response. scf.uhf method of PySCF package, the default behavior is to calculate the ground state, not the first excited state. But Amun already knew that. Imagine if Amun now asks, are you sure it's not the first excited state? I guess ChatGPT could say, apologies for the confusion. I go back to saying that it's the first excited state. And I've seen ChatGPT do things like that. And I've seen ChatGPT apologize for the confusion when the original answer was correct and the user was just asking for clarification, and ChatGPT just clarifies, just writes the same correct thing but in a slightly different way, and still says, I apologize for being wrong the first time. It says, I apologize for giving you the incorrect answer the first time, even though it was correct. So it's sometimes apologizing when it shouldn't be. Amun asked, how can I calculate the CCSD-T energy? ChatGPT says to calculate the CCSD parenthesis T energy, blah, blah, blah. But CCSD parenthesis T is a different method from CCSD-T. Here, you're including full triple excitations. Here, you're including perturbative triple excitations. So it's giving the wrong answer. It doesn't know what CCSD-T is. It's not actually as intelligent as a human that's done a PhD in quantum chemistry. Dayan asked, can you list diatomic molecules which have a quadruplet ground state? And ChatGPT says, certainly, here's a list of diatomic molecules that have a quadruplet ground state. Wrong, 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 wrong. All of these are wrong. Oxygen has a triplet ground state. Chromium dimer has a singlet ground state. It's also wrong when it says that these diatomic molecules possess a total spin quantum number S of 3. What's the spin multiplicity of a molecule with spin quantum number S equals 3? Remember, it's 2S plus 1. 2 times 3 plus 1, that's 7. This is a septuplet. So not only is it wrong, none of these are actually septuplets or quadruplets. They're triplets and singlets. At least the first two are. But it's also wrong about the definition of a quadruplet. It doesn't know. But even if it used that definition of quadruplet, it's still wrong. So it's just completely wrong. Dayan asks, are these all of the diatomic molecules that have a quadruplet ground state? And ChatGPT says, no. There's plenty of other diatomic molecules with a quadruplet ground state. Nitric oxide, nitrogen dioxide. Wait a minute, nitrogen dioxide? Nitrogen dioxide is a triatomic molecule. Some of these are not even diatomics. NO2, SO2. These are not even diatomic molecules. How can they possibly be? How can ChatGPT possibly call these diatomic molecules when there's clearly 3 atoms there? ChatGPT does not know what it's doing. It just doesn't know. It's like a photocopier. Remember in the primary school students class I had on machine learning? I said you don't want to just be copying the potential. When you're fitting a potential to an analytic function, you don't just want to be copying it point by point. You want to actually learn something so that you can predict other parts of the potential. And the large language model has learned something, I guess, but it hasn't learned the difference between 2 and 3. Or at least in terms of chemistry, 2 atoms and 3 atoms. It doesn't understand GCSE level or grade 11 chemistry, just balancing equations and chemical formulas. It just doesn't know that basic science. Tejas asked, what is the G6MS group? ChatGPT-4 didn't know. It says, I'm sorry, I couldn't find any information about this. I could have also shown you what ChatGPT 3.5 gave. It actually gave the wrong group. It said that G6 group was IH or OH or something like that. So it actually gave the wrong result. And then when he said, where did you find that? It said, sorry, I was wrong. It's not the OH or IH group. With GPT-4, it just straight out says, I don't know what it is. And that's maybe fair because group could mean a lot of things, okay? You have a group of people going to the cinema together. That's different from group in group theory. So he asks, what is the G6 molecular symmetry group? And it still says, I'm sorry, I couldn't find any information. But molecular symmetry is a fundamental concept in chemistry, okay. If I search on Google, G6MS group, I literally only get 3 results. I don't know why I'm only getting three results. That's, well, I guess not everyone calls it G6MS group. Maybe they call it G6 molecular symmetry group, or they just call it G6 and you know that they're talking about the group. They might say G6 character table because they're giving you a G6 character table, and if you know any group theory, then you know that they're talking about a G6 group. So maybe they don't always say G6MS group in that exact phrasing, but there's 3 results here that say exactly G6, well, here it's G6 equals MS group. So these 3 results, the last one's from International Symposium on Molecular Spectroscopy. That's the conference that I went to last month. If you remember, I was away, I went to that conference. Next year, I hope that all of you can join me in going to that conference. And you can present a talk there. There were undergraduate students giving talks at the ISMS conference last month. And there's no reason why next year you can't give a talk at that conference. But I digress. The other result here is a 2020 paper by Schwann. 12 citations, good paper. G6MS group. And then the first example here, it's from Google Books. A famous book by Phil Bunker and Per Jensen on molecular symmetry and spectroscopy. And when I look at that book, when I click that button, I get G6MS group in this book. And here is the G6MS group. Okay, that is how it is defined using mathematical symbols. So ChatGPT 1, Google 1. ChatGPT 1 for the oxygen atom charge. Google wins this time. ChatGPT loses big time. So, clearly, ChatGPT is doing a poor job on every question we ask it, except for that one question about the charge of the oxygen atom. You can look through the Discord server. I don't think there's been any cases where ChatGPT gave the right answer. Although maybe people have been using it all along and haven't been telling me. Maybe they've been using it to find out how to use Avogadro or something like that. But from what I've seen, it's just been wrong every time except for Searchow's example. So what about domain-specific chat GPTs? Okay, OpenAI has this article, How to Give Domain Knowledge to ChatGPT. On Medium, there's this article, Building a Domain-Specific Chatbot Using GPT-3. On GitHub, there is this ChatGPT Turbo. On Hugging Face, which is an open source artificial intelligence organization, a bit like OpenAI, but it's actually open. Domain-specific ChatGPT, they tell you a little bit about that. So it's not going to take you long to learn how to make a domain-specific ChatGPT. In fact, there's a YouTube video, I think it's 2 hours long, where they show you how to build ChatGPT from scratch. We all know how to do it. The technology is nothing particularly novel. It's the way that it was engineered very, very well. That's what makes it stand out from the other GPTs or large language models out there. So ChemGPT will give the correct answers for all of those examples that I gave you just now. ChemGPT can be trained on Matter Modeling Stack Exchange, which is a platform that I created, which now has more than 3,000 questions and 3,000 answers. There's a lot of data, so just like GPT-2 was trained on Reddit posts, you can start with Matter Modeling Stack Exchange and get all the information from my answers and other people's answers. You can also use Google Books, I suppose, but that will not give you the entire books. That will give you part of the books. But there's open source books out there. There's Chem Texts or something like that. There's Libre Texts or something like that. And there's a chemistry. There's a lot of chemistry textbooks that are on there. There's Wikipedia articles. There's a lot of things in the open domain that we can use for training ChemGPT. Let's talk about huge databases in chemistry, because for Stable Diffusion version 1, we needed 600 million images. Do we have 600 million energies, for example? What if I want to ask ChemGPT, is there a pair of molecules such that one of them is a C2V molecule and its barrier is twice as big as the dissociation energy of a D2H molecule? Is there any such pair of molecules? I'm sure if I ask on Google, it's not going to give me the right answer. You can try it on ChatGPT. I'm sure it won't give you the right answer based on the fact that it didn't even know, it didn't even know basic group theory. Well, it knew basic group theory, but it didn't answer some of those previous questions, even some very easy questions. It couldn't answer them. So if I want to answer a question like that, I want two molecules such that the dissociation energy of this one is half of the barrier, the size of the barrier of some other molecule, then I'm going to have to know a lot of energies. So let's start training a ChemGPT, not just with the knowledge that we have on Matter Modeling Stack Exchange, but also energies. I want to be able to ask, are there any molecules with a lower ground state energy than the chromium dimer, or higher ground state energy than the oxygen dimer? I want to be able to answer questions like that. So an easy way to do that is to calculate lots and lots and lots and lots of energies. In 2010, this is more than a decade ago, in 2010 there was a huge database in chemistry that was published in this paper. It was called the GMTKN30 database. It's a database constructed from 30 different databases. These are 30 different databases. One of them has 99 atomization energies. The other one has ionization potentials for 36 molecules. One of them has electron affinities for 25 molecules. One of them has proton affinities for 12 molecules. One of them has barrier heights for 26 different pericyclic reactions. One of them has reaction energies for this entire BH76 dataset, 30 of 30 molecules. This one has radical stabilization energies, 43 of them. Isomerization energies, 34 of them. There's tons and tons of energies here, all different types of energies, and they put all of these references together, all of these data sets together, and in the end they only have 1,218 total energies. Okay, so that's quite sad. We have 30 data sets all combined together and only 1,000 energies. But this is 2010, so let's not blame them. This was actually a very, very big landmark paper. They tested these they calculated these 1,000 energies on 47 different functionals. For those of you that are familiar with density functional theory, instead of trying to solve the Schrodinger equation, because the wave function grows exponentially as you increase the number of electrons in the system, the wave function is just extremely difficult to work with. So instead, there's something called density functional theory, a different route to getting energies that avoids using the Schrodinger equation. It avoids wave functions. And essentially, you're fitting these density functionals so that they work very well. And the simplest of these density functionals, the LDA density functionals, they're wrong by 12 kilocalories per mole on average compared to the benchmark data set. The GGA functionals are a little bit better. The meta-GGA functionals are a little bit better. The hybrid functionals, including the famous B3 lip functional, is a little bit better. And then the double hybrids, back in 2010, they managed to get down to 1.8 kilocalories per mole discrepancy on average. Now, in 2023, with better machine learning approaches, density functional theory can give even better energies here on average. But it's still not better than 1 kilocalorie per mole, because if you see here, the reference method, the benchmark against which they are comparing things, is CCSD parenthesis T in a complete basis set extrapolation. CCSD parenthesis T, they're almost always using that. Sometimes they use experiment, but you can't do millions of experiments on millions of different molecules, and it's just going to take too long, it's going to be too expensive, and it won't even be that accurate sometimes. But CCSD parenthesis T is known to be only accurate to about 1 kilocalorie per mole on average. Sometimes it's even worse, sometimes better. So they're not going to get better than 1 kilocalorie per mole here. But we can make a database of experimental energies, and when we don't have experimental energies, we can do better than CCSD parenthesis T. You've done CCSD parenthesis T calculations on your laptop. Now on the supercomputers, you can do CCSD-T. That's full triples, not perturbative triples. You can do CCSD-TQ. So I'll teach you how to do that. We'll be doing that soon. AI Energies is a database on GitHub that I started in 2018. Now this has grown to having 300,000 systems, 60,000 molecular geometries. A lot of you might be familiar with this 60,000 molecule database that last term, a couple months ago, we were talking about that database. With 60,000 molecular geometries, if we calculate the energy of the neutral molecule, and then in PySCF we change charge equals 1, charge equals 2, charge equals -1, charge equals -2, then we have 4 molecular ions at each geometry. So we have 5 molecular systems for each of these 60,000 molecular geometries. That's 300,000 systems. And then we can do lots of energy calculations. UHF, RHF, ROHF, generalized Hartree-Fock, MP2, CCSD, CCSD parenthesis T, CCSD full T. We can do calculations with several different basis sets. We can do complete basis set extrapolations. Overall, we have more than 1 million energies available. Some of these are still being calculated by you, everyone in the audience. Soon, we will have more than 1 million energies. Then, we will have more than 600 million energies. Eventually, we'll have enough data to train ChemGPT so that it knows energies when you give it the geometry or the name of the molecule or some other information. Then it doesn't have to solve the Schrodinger equation, and it doesn't even have to use density functional theory. As a basic computational complexity analysis, I'll tell you that solving the Schrodinger equation, some people call it 2 to the n scaling, exponential scaling. It's really more complicated than that, but let's just say it's 2 to the n, an exponential. Density functional theory is n cubed, so it's a polynomial. It's a lot better than the Schrodinger equation, but it's still n cubed. That's still a big deal. With machine learning, we can get linear complexity. You give it the molecule, and it gives you the energy. Linear complexity. Even constant complexity, depending, like ChatGPT is not giving, the cost is not necessarily linearly proportional to the size of the input. So we could get linear or constant computational complexity when we use machine learning versus when we're using density functional theory or wave function-based approaches like coupled cluster. This is what AI energies looks like. There's AG2, ALF3+, ALF3, AL3+, AL3. These are all just molecules in alphabetical order. That's what AI energies looks like. So now let's talk about the geometry database. Okay, one thing is the artificial intelligence energies or ab initio energies database. Now let's talk about the geometry database. Geometries are also important. Let's say I want a molecule such that the bond length is less than 2 angstroms, the average bond length for all bonds. Or maybe I want a molecule with a very big angle and I want to be able to ask that to ChemGPT. Maybe I'm designing a drug and I want a molecule with certain properties, certain geometry, certain structure, certain shape. A shape that binds to proteins. The geometry database could be an example of that. Now, there exist geometry databases. You've all seen this geometry database, Landolt-Bornstein. Here they have a bond length HH, AgCl. They have these bond lengths. Here you have another molecule. You have bond lengths. You have bond angles. Here you have another molecule or a van der Waals complex. Here you have another molecule, different angle, different bond length. Here you have another molecule. Here they give you a dihedral angle and some bond angles and bonds and bond lengths. Now, what's the problem with this data set? Lots and lots and lots and lots of problems here. First of all, you can get this access to these data sets, but it costs $5,000 for this book, $7,000 for this book, $3,000 for this book. And there's dozens of books for these geometry databases. Each book is like, these are all the geometries that were published in scientific journals between 2006 and 2019. And if you want the geometries from 2002 until 2006, then you have to look at this other volume of the books, of the book series. And if you want 1985 to 1991, then you have to look at this other volume. So that's why you're not finding every molecule in there. So it's expensive. There's a lot of books. If there's 10 books, $5,000 each, that's $50,000 right there. These books are expensive compared to free and open source GitHub databases. They're slow to load. Okay, imagine PDF, opening a 900-page PDF. That's just one of the books is a 900-page PDF. That's slow to load. Imagine opening that PDF versus opening just a plain text document. It's not very copy-pastable. When you're copying and pasting things from PDFs, you always have to double check that the 5 doesn't become an S. Or, you know, there's a lot of characters that are not always copied and pasted correctly. With plain text, the copy and paste always works because the copy and paste is designed for plain text. These books are also not very organized or organizable. How are you going to organize these books? If I ask you for all molecules with 5 atoms, you're going to have to write some Python script to go through and parse the molecular formulas. And the molecular formulas aren't in an obvious place. It's not like this is in a database, in a text file that it's like formula equals AsH2O or formula equals H2OS. They're giving you basically formulas in this top right corner, and you have to tell the Python script to look in that location, and even then it might not always be in the same location. Sometimes they have the group here, the point group symmetry given here. Sometimes they have some other stuff given there, so you don't always know where it is. And you don't always know how many of these molecules are on a single page. So it's not like you go through each page and look in the same spot. It's like some pages will have 2 molecules. One of them will be in the top right corner. The other one will be in the middle of the page. So it's very hard for computers to read this data, and it's very hard for them to organize the data. But if we have a plain text file, we just have a script that just goes, it just says formula equals whatever, and then you look for where it says formula equals and you get the formula. And then you can easily just compute the length of the formula or the number of atoms in it. Very easy to do. And so you can organize it. And so if you want to do a calculation on a data set full of organic molecules, you can find all the organic molecules. If you want the molecules that contain sulfur, then you can find all the molecules that contain sulfur. Easy. This is what the geometry database looks like at the moment. So I have name equals AGARI. So if I want that molecule, I just search for where name equals that. And then I have bond lengths. ARAG has this bond length. AGI has this bond length. And because this molecule has C infinity V symmetry, point group is C infinity V, I know it's a linear molecule, so I know the angle is 180 degrees. So I don't even have to put that. Likewise for AGHS, I have the bond length here, and an angle. And now it's time to add all of these molecules to this database. That way we have a geometry database. That's the first step to making a ChemGPT. So Sochow has added molecules that look like this. His first task was to make a Z matrix for this molecule. So using these bond lengths and bond angles, notice they don't give you dihedrals, he figured out all of the dihedrals for this molecule. He has a code that generates the Z matrix using this data. And then he entered this data into the geometry database, and he not only did that, but he did it for all molecules that have this shape. So you can see tellurium tetrachloride, tellurium tetrafluoride, tellurium tetrabromide probably also exists, tellurium tetraiodide. You have all the halogens. You might have, instead of tellurium, you might have something else. So there's lots. You can imagine thousands of molecules with this shape easily. Just replace tellurium with 100 different atoms, maybe not 100, maybe like 50, I don't know. And then these atoms, they change, and they don't always have to be the same atoms. You can have, because this is the axial bond length and this is the equilibrium bond length, so you could have like 2 fluorines here and 2 chlorines here. And the combinatorics tells you that there's going to be lots and lots of combinations. In fact, if you had different isotopologues, that means a molecule with different isotopes of different atoms. You have 2 different isotopes of chlorine here versus over here. Then you'll have different bond lengths, and therefore you'll again have a different molecule. So that code, he spent a lot of time understanding how to make a Z matrix for this molecule. But now that code that generates the Z matrix for this molecule can be used on thousands of molecules. So he is focusing on molecules with this shape. Dayan is focusing on molecules of this shape. Dayan did the Z matrix for this molecule. There's lots of molecules with this structure. B2H6, AlBr6, Al2Br6, Al2Cl6, Al2I6. There's probably also Al2F6, fluorine, because these are halogens again. So lots of examples and lots of molecules to enter into the geometry database. Harvey is focusing on molecules like this. So entering molecules into the geometry database, anything shaped like this. And not just that, but the focus is going to be on this type of molecule for the rest of the summer. Okay? So calculating the dissociation energy, calculating isomerization energy. That's the energy, the barrier energy between this isomer and this isomer. The atomization energy, the spectrum, like a lot of different things can be calculated for each of these molecules. Geometry optimization. You're going to learn how to basically do every single possible thing in quantum chemistry for your molecule by the end of the summer. Tejas will work on molecules that are like this. That's the molecule that Tejas has been working on in terms of building a Z matrix. Next, you do the geometry optimization, see if the coupled cluster bond lengths are different from the experimental ones, things like that. Doing atomization energies and all sorts of things. So all possible quantum chemistry calculations that someone with a PhD in quantum chemistry would know how to do, you're going to know by the end of the summer. You're going to do these calculations. But most importantly, you find all the molecules for which those calculations or those input files would be relevant so that we can do it in a batch. We can do 1,000 molecules at the same time instead of doing 1 or 2 molecules at a time. Amun is focusing on molecules like this. Abdul is working on molecules like this. Hemant is working on molecules like this. Dulain is working on molecules like this. And I think this might be the last slide, so I thank you very much for your attention. I do understand that entering this data into the geometry database, it's the most tedious thing that I will ever ask you to do all summer. This summer, I will not ask you to do anything more tedious than entering data into the database. I know and I'm completely aware of how tedious and boring it is. However, this is what needs to be done. ChatGPT doesn't get made without human intervention, without manual curating of the database. The database has to be made by someone, and it takes time. And no one's done this. We're going to make the open source project so that others don't have to do it in the future. There will be a lot of fun things to do. You're going to use supercomputers. For each molecule, you're going to calculate energies with various different methods, various different basis sets, and you're going to see how it converges. You're going to learn a lot about how to do quantum chemistry calculations, how to use supercomputers, how to do massive calculations with hundreds of cores. You're going to learn all of that, but at the same time, you also do need to do some tedious things. It's research. You may have heard of the term lab rat. Unfortunately, when you're an undergrad student or even a PhD student or a postdoctoral researcher or even a professor, you will be doing a lot of tedious work. Unfortunately, that's how it is. When you're writing a paper, you're making tables, you have to make that table. Whoever, Stefan Grimme is a very famous professor. He invented a lot of the functionals. He invented double hybrid functionals, which are these very good ones here. But you can see this database, this slide where I have table 1, description of subsets, this table was made by someone, and this is tedious to go through every data set and count the number of molecules and calculate all these energies and enter this into LaTeX. That's a lot of tedious work. Professors do tedious work too. And whoever enters the largest number of molecules into the geometry database, if you enter 100 molecules into the database, I have promised that I will enter 100 times more than you. So if you have entered 100 molecules, I am going to enter 10,000 molecules. Maybe I'm overestimating my capabilities here, but if you are entering 100 molecules into the database, I will be entering 10,000. There's enough molecules for everyone. Okay? So please don't get discouraged by how tedious some work is in research. I'm warning you ahead of time so that you don't get depressed later on when you feel like this isn't something that a highly intelligent person is needed for. Well, really, if it's that easy, then let's see you add 5 or 6 molecules. So far, no one has done anything other than Suchao. So let's first get there, and then let's see if you can do 100 molecules. I don't think that's too much to ask, considering that this is research. And even as a PhD student, there will be situations in which you'll consider yourself a lab rat. That's just ultimately how research works. So thank you very much for your attention. All slides are available. Oh, I gave you the PDF in Discord, but they will be available on GitHub as well. Now I'll take any questions from you.